All right, here we are for homework number 9. Let's see how this goes. All right, we're using the direct comparison test to determine whether this series converges or diverges. So we got to pick a more familiar series that's very similar to this. I'm going to go with, here, let's use this color. Let's compare it with, 1 over n squared. Now, it wouldn't hurt to write down a few of these terms just to make sure that we're, actually indeed comparing the way that we would want to. So this 1 over n squared is going to be a convergent p-series. So we're hoping that that convergent p-series is larger than the thing that we have originally. Let's check a few terms real quick. When n equals 1, we have 3 over 1, which is 3. We'll call it 3. When we got 2, we've got 4 over 8. When we got 3, we've got 5 over 27. All right, let's take a look at these real quick. We'd have 1. We would have 1 over 4. We would have, good grief, 1 over 9. Oh, and in each case, this series that we picked is actually smaller. So this won't do for the direct comparison test. I mean, yeah, it would be fine to do the limit comparison test. But we want to use the direct comparison test. Yeah, right now we're small. Suppose one thing I could do is just, cut off the first term, let's say. Transform this first one See, there are a lot of, what I'm getting stuck on right now is that there are a lot of different ways to do this. Is like, it would have been easy to split that up into it would have been easy to split this up into 2 different fractions that would both be convergent p-series, and you'd be done with the problem. But yeah, we have to use the direct comparison test. What's a good way? Oh, what happens if I just put a 4 on the top? That's all we have to do. Yeah, shoot. If we just multiply this one by a constant, let's just say 4. Then we'd have a 4 here, we'd have 4 over 4, and we'd have 4 over 9. Then we're direct comparison. Good grief. All right, so just the plain old 1 over n squared will not do for the direct comparison test. But if you multiply the whole thing by 4, then you are greater at every single stage, and that would continue going forward. So that works. All right, we will keep going. Use the limit comparison test to determine whether this series converges or diverges. Okay, limit comparison. So again, we want to come up with a more familiar series that looks like this one, or at least would behave like this one. We've got a square root of n on top, square root of n squared on bottom. That means net-wise, we're in a ratio of 1 to the square root of n on bottom. We've got one more power of the square root of n on bottom. And for the limit comparison test, we look at the ratio of these two sequences. Honestly, which one goes on top? Do I remember that offhand? It doesn't really matter as long as you interpret the results appropriately, but let's go ahead and put the original sequence on top, or the original series on top, and see what happens. So let's take a look. We're going to look at the ratio of their terms. So square root of n over square root of n squared plus 1 over 1 over the square root of n. Cool. And technically, we are looking at the limit as this monstrosity as n goes to infinity. All right. Then we would actually do this division. Which is really a lot like multiplication. We've got n over square root of n squared plus 1. Boom, boom, boom. Yeah, and then the way that the book has been doing this, rather than L'Hopital's rule or anything to figure out this limit, we've got something that looks like infinity over infinity here. It's just to divide through by n on top and bottom. So 1 over square root of 1 plus 1 over n squared. And as n goes to infinity, that one, goes to 0. And we're left with this limit equaling 1. So now, let's think about what does that mean in terms of the limit comparison test. Well, that means that these two series are converging and diverging at a very, very similar rate. Overall, it means that it's a good comparison, and since our familiar series is a a divergent p series with p equal to 1/2. This one diverges as well by the limit comparison test. Solid. Okay, that's 10.4. Moving on to 10.5. See if we can get this before our activity starts in 10 minutes. Use the ratio test to determine whether this series converges or diverges. Okay, ratio test means that we are putting, let's do the n plus 1th term over the nth term, and we'll look at the limit as n goes to infinity. Here we're not making up another series to compare to, so this is not a comparison test. This is a ratio test. We're looking at the n plus 1th term, so n plus 1 times 1/2 to the n plus 1 power over n times 1/2 to the nth power. And let's see what we can simplify. Yeah, this basically breaks down to this Nope. 1/2. The n plus 1 over n definitely goes to 1. I mean, we could divide everything by n and see that. And so this ratio test ends up being 1/2. And that's because the geometric part of this is the, I don't know, the dominant part. So by the ratio test, if we're converging towards 1/2 as a ratio, this thing converges. Just like, it's very similar to a geometric series here. Yeah. Okay, moving on to number 42. Oh man. The image is broken. I'm not going to know the instructions. Use the root test to determine whether the series converges or diverges. Root test. Got it. Here we take a look at the limit as n goes to infinity of the nth root of this. For my own sanity, I don't like that that's 3 to the n minus 1. I would love it to be n. And so in order to give that another power, I'd need to pull out a 1/3. So I'm going to do this real quick. And here, root. I'm going to pull out a 1/3 so that I can call this 3 to the n power. And then this is n to, oh gosh. This is n to the n power. I'll call you right back. Okay. That was Dr. Eisenbeck calling. I want to finish this. Daggone it. All right, I don't know if I have time. Oh, maybe I should call him back. Anyways, this is getting really close. We have the nth root of 1/3, which is very small. Or maybe it, I don't know, does it go to 1? I have no idea. I'm distracted now. Okay. Times 3 over n. The nice thing about all of this is that as n goes to infinity, we approach 0. And so, yes, by the root test, this thing will converge. All right. So, moving on. Determine whether the given series converges absolutely, converges conditionally, or diverges. Use any convergence test discussed so far in this chapter. Okay. Let's think about whether this converges as an alternating series. And then we'll have to see if it converges absolutely as well. Okay, converges as alternating series. Do we pass the 2 criteria? So the first criteria is, does this decrease monotonically? And I think it's pretty obvious that yes, it would. Yeah, the bottom increases faster than the top, so this fraction is decreasing. So we're good here. And for the second part, does that approach 0? Yeah, so limit of an as n goes to infinity, does that equal 0? And yes, it does. That would go to 0 overall. So I would say yes, that does converge as an alternating series. As a... Absolutely. Okay, so converges absolutely. The answer there, I think, is going to be no. We'd be looking at this series, which I think, at the very least, if we use the limit comparison test on this guy, we'd be using the harmonic series as a comparison, and using the limit comparison tests, we would come up with something that looks like n squared over n squared plus 1, and that limit comparison test would equal 1 in the end. So these two things diverge together. So yeah, I just talk through the limit comparison test. It would equal 1. So both diverge there. So the overall answer to this question is that this converges conditionally. Kate claims that this series converges by the alternating series test, Leibniz's test, because it's an alternating series of that form and all of those approach 0. Those two things are true. Is she right? Why or why not? This thing does not decrease monotonically. So AN doesn't decrease monotonically. And that would be enough to say that Leibniz's test doesn't apply. I think something interesting here to note is that if we were to look at here all of the odd indexed parts, we get something that looks very much like the harmonic series. And if we look at the even indexes here, we have a convergent P series there, something that looks very much like that. Where, this thing diverges. This part converges. And so I would be pretty confident that this thing diverges overall. But yeah, the fundamental reason that you can't apply Leibniz's test there is that AN doesn't decrease monotonically. All right, I'm going to call Dr. Eisenbeck back. I hope you had fun doing homework number 9. I'll see you very, very soon for the activity. Okay, bye.